morning here, we're lucky enough to have David Waterman, one of the developers and maintainers of dials, give a walkthrough here. And so basically kind of the intent here is for you guys to kind of listen, have kind of the data up and move along, but really kind of spend your time listening to what David has to say. If you look at the schedule that was up previously and on the Slack channel through various communications that we've had, after David's tutorial, we do have an actual dedicated time for you guys to work on. During that time, I'll send you the Slack message a little bit of a cookbook. So don't worry too much about taking notes. Just kind of take this first morning session to kind of absorb the information. Yeah, I don't think I have anything else, Christina. Anything come to mind right away?
I don't think so. When it comes to actually working on your computers, I deployed some power strips around the room, so hopefully everyone has power they need. There's a spare pack if you need it.
Yeah, I don't think I have anything else. So, David, go ahead and take it away.
Okay, thanks, Dan. You hear me okay?
Yep, we're good.
Yep. Super. Okay, so yeah, thanks to all the organizers for inviting me again to this really excellent symposium and workshop. I've got this first session, first hour and a half, I'll split between some slides I've got about dials and its adaptation to ED methods, and then, like, as Dan said, a walkthrough on with one of the tutorial data sets. So yeah, my slides. So my name's David. I'm part of the CCP4 core team based at Harwell in the UK, and we're right next to the Diamond Light Source synchrotron, which you can see on the header of all my slides. So I've got a general introduction slide about MicroED, and this is really quite similar to material that Tim presented yesterday, but I like to show this as a reminder, particularly to X-ray crystallographers, of the vast scale difference between the two methods. So really, with X-ray crystallography, even at the best microfocus beamlines, you're limited to crystals of down to, well, 5 microns is a bit big. At VMXM and Diamond, you can get down to just under a micron to a side for crystals. But this is still far too large for the MicroED method. So nanocrystals that we use in that method are really 1,000 times smaller in volume to get it down to the upper limit of usable thickness for that method. And that makes them literally vanishingly small, because the thickness of the crystal is smaller than the wavelength of visible light. So a point that I wanted to make about the software for MicroED is that we can split the software into sort of packages that are specialized for the method and those that we've borrowed from X-ray crystallography. And really, this is a consequence of the fact that the fields have developed quite independently over the past few decades, and the software development reflects that. So looking at specialized ED packages, you have programs like ADT, 3D, and RED, and then PET that was presented by Lukasz yesterday. And then if we look at software that was borrowed or adapted from X-ray crystallography, you have MOSFilm, dials, XDS, and then more recently Chrysalis Pro, which has been used for many years on Rigaku X-ray diffractometers, is now adapted for their Synergy ED instrument. And really what has enabled this is that there's been a convergence of the methods in recent years from sort of various sort of tilt-based or discrete tilts or precession-based electron diffraction methods towards a more standard continuous rotation, random orientation method, which is really exactly what we do at X-ray beamlines. So that's why software for X-ray data processing can be used for MicroED. And this has also been helped significantly by the existence of fast, low noise detectors, like Clemens presented yesterday, which really allows this continuous rotation method. So a few notes about what DIALS is. The name is an acronym. It stands for Diffraction Integration for Advanced Light Sources. And considering the debacle about whether to call this method MicroED or 3D-ED, I can say it is hard to name stuff. Because now, of course, we're working not just with light, but also with electrons and even neutrons now as a current development in the DIALS team. The joke I made, though, is that if we'd called it Diffraction Integration for Advanced Particle Sources, then the acronym would be DIPERS, which doesn't sound particularly good. So anyway, we set this project up. I still think of it as the new kid on the block for data processing, but really it's 15 years of development now, which was set up to address modern challenges in X-ray crystallography at the time. But really these challenges, things like the fast low noise detectors and microfocus beamlines are quite standard now in MX. And over the years, it's developed into an international open source collaboration. The main teams are the DIALS East team based at Harwell, and then also a team at the LBNL in Berkeley, the DIALS West team. But we've actually had contributions from developers from all over the world. I think the list in the authors file that comes with the software is something like 30 plus names long now. So the idea of this community resource is that it's not just software developed for Diamond or Berkeley or even CCP4, but it's developed really for anyone to take and to adapt and to develop themselves. And of particular importance to the US audience, Aaron Brewster at Berkeley recently got R24 funding for DIALS as a national resource, which explicitly includes support for MicroED. So there's some information about that on our website, but yeah, do get in touch with Aaron about that. Right, so the DIALS package was developed as a very general framework and toolkit. It's not a black box that you pour images into and you get processed data out the other side. It's an extensible framework that can be adapted to various different types of experiments. And that's how we handle single crystal rotation and serial experiments in macromolecular and chemical crystallography and time-of-flight neutron crystallography. So by using this toolkit approach, we can really adapt to the different types of experiments. And as I mentioned, we're source agnostic these days, so handle X-ray, electron, and neutron probes. So these are the essential tasks in diffraction image data processing, and this is probably familiar to anyone who's used any crystallographic data processing software. All the different programs have some version of these tasks that differ really just in implementation details. But one of the more unusual features of DIALS is that each of these tasks is discrete and run as like a single unit. But what I mean by that is that, for example, all of the refinement of the geometry model is done ahead of integration. And that's different to, for example, XDS, which operates using a sort of moving window that goes through the data set, refining a little block and then integrating and then moving to the next block. The idea with DIALS is that we have a global model for what the experiment is prior to going into integration, which allows global modeling of not just one data set, but multiple data sets together, but also enables a high degree of parallelization. So the integration task can be split over many cores at a high performance computing facility because there's no unknowns left. Having refined the whole model, you can go ahead and split over all the images and get the same result as if you were running it on a single computer. But another sort of reason for this way that the program has been laid out is that it's part of the modular philosophy. where each of these tasks is handled by a separate command line program with a recognizable name given by the task it's performing. So yeah, to talk about that command line interface, the main interface to dials for MicroED work, at least, is using that command line alongside use of some graphical reporting programs. And this means that dials is very well suited to scripting, because if you find a set of commands that works well for one data set, you can very easily put that in a script and run it on the next data set and so on. And while GUIs are nice, they're sort of a nice user-friendly way to get into software. It's the GUI that we have for dials. There's one developed by CCP4 called DUI, not driving under the influence, but the dials user interface. And that's not really fully adapted to MicroED yet. So I prefer to use the command line interface. And that's what I'll show in the walkthrough and what's being used in the tutorials. So yeah, the command line interface works very well on Linux or Mac, where you're kind of used to using bash terminals. But you can even use the command line on Windows. You can build dials for Windows and run it natively there. It's just a bit more awkward. But I think as maybe Dan mentioned yesterday, these days with WSL2, you can have a very functional Linux system on a Windows PC, and that seems to be the best way to run this kind of software. So in total, the toolkit's quite large, but most standard data processing tasks will only use the sort of same basic set of programs which are listed here. So yeah, the use of dials for MicroED really began in 2018 when Max Klabbers, who at that time was at Jan Peter Abraham's group, visited me with some data from an orthorhombic lysozyme nanocrystal. And there's a picture of that crystal. And at the time, I think that was the smallest single protein crystal to be used in a structure solution. So it's something like 600,000 unit cells in total. We worked together to figure out how to replicate his XDS processing of the data. And in doing so, we had to add quite a few features to dials. So we added in an elliptical distortion correction because some of his images had quite distorted diffraction patterns. We added in modeling for drifting beam center, various refinement diagnostics to handle the fact that refinement of the detector and unit cell simultaneously is very difficult. And with that, we could process the data. And since that time, I've added various other features. So, for example, image format readers for all sorts of EM image formats, new spot finding methods for integrating detectors used in MicroED, and tools for determining the rotation axis, determining better beam center, serial ED tools, and so on. And together, in that sense, dials is not really, it's no longer merely borrowed from X-ray crystallography for MicroED, but we're specifically targeting that method too. Nevertheless, I'd admit it's not fully tailored for MicroED. Sometimes you have to work around some X-ray defaults. And there are some things that we lack, so we can't yet handle things like precession experiments, although we're looking into supporting that soon. And as I mentioned, the GUIs are not quite there yet. They're a bit weak in comparison with software like PETS and Chrysalis Pro. And if you're an XDS user as well, you would notice that dials is not quite as fast as XDS. We can't cope with this sort of high performance raw Fortran coding that XDS has, but we are, I think, more flexible. So positive points are it's open source, it's extensible, flexible. Anyone can take it, use it, modify it, even commercial companies. It's very good for scripting, data processing, and has very good handling of multiple crystal experiments. And of course, it's quite familiar to structural biologists, well supported by for the MX community by Diamond, by CCP4, and our colleagues at LBNL, and places like SB Grid as well also distribute. So one question is, why do we need adaptations at all? In other words, why is it problematic to process MicroED data? And like with the crystal size comparison, as a trained X-ray crystallographer, I like to think about the comparison always between the MicroED experiment and the X-ray MX experiment. So here's the diffraction geometry represented in the laboratory frame for both experiments. And for X-ray MX, we have a very large and very expensive detector, which would be relatively close in to the crystal. Scattering all occurs at scatters out to high angles. Crystals probably larger than the beam, or maybe you could beam size is adapted to crystal size. But in comparison, for MicroED, we have really a very tiny detector that's effectively very far away. Of course, that isn't a real distance, but that's the effective direct path distance of the rays as they travel through the microscope lens system. The contrast is we have a very small crystal. It's probably completely bathed in the beam if it's a nanocrystal, unless you're doing fib milled experiments, in which case you've got a sort of a wide crystalline field from which you can pick different points to collect data. And we have very small scattering angles. But data processing people like me like to think in terms of reciprocal space rather than real space. So here is the description of the diffraction geometry and reciprocal space using the famous EVOL construction. So for X-ray diffraction, we've got a reciprocal lattice, which is this gray mesh. And that extends out to some resolution limiting sphere here, which I've marked in red. And the figure here is assuming an isotropic resolution limit of 1 angstrom. The blue sphere is the Ewald sphere, which is telling us which reflections are excited at any one time. And S0 shows the incident beam in reciprocal space. And S1 is one of the scattered beams that's where the Ewald sphere intersects with a point on the reciprocal lattice. And this is a reflection that's a 2 angstrom resolution reflection because it's halfway along the radius of the resolution limiting sphere. And you can see that with the X-ray construction, a single image, a single image is the projection of the 2D surface of the Ewald sphere up to the intersection with the resolution limit sphere. So we've got this surface here, which will be projected out onto some detector on the right of the screen. And although that's a 2D setup, that's a 2D, if it's a still image, it's just that surface. That construction still contains information about the reciprocal lattice direction along the beam because of its curvature. Whereas if we compare with the MicroED situation, it looks like this. The Ewald sphere suddenly has a much larger radius, so 40 times larger for a 200 keV beam. And now that single, that slice through the reciprocal lattice is now almost a plane, not quite, but nearly a plane. And that means that this lattice direction parallel to the incident beam is essentially not sampled at all, which makes it hard, if not impossible, to index all 3 basis vectors from a single image. And also, there's hardly any difference in the scattering angle between the rays, which means that the detector distance is very poorly determined by the data. So you can move the detector in and out, and it hardly affects the positions of the spots. So that's the real challenge in the geometry. And it's the almost flat Ewald sphere and the very low diffraction angles. And as a consequence, you get difficulties jointly refining detector and unit cell, and the parameters for those are likely to be poor, particularly if you've got an error in the calibration, the detector distance that will appear in error in the unit cell parameters. As mentioned, Indexing from a single image is very challenging, and it's also a challenge to determine the direction of rotation. And the beam center might be unknown, and it can even drift. None of these things are really a problem with modern MX synchrotron beamlines, but we have to have to counter all of these effects dealing with electron diffraction. And the lens distortions can introduce systematic error in observed positions. Now, these challenges, some are more important than others. So with good data these days, I find that you don't really have to model the drifting beam center, assuming it's drifting only a few pixels. And you don't often have to model lens distortions. I think the only time I ever did it was with that data from 2018 from Max. But the other problems still exist. However, yeah, in my experience, the biggest obstacle and annoyance to all this is really prosaic. It's just getting the data correctly into the software in the first place. So unfortunately, as mentioned by Clemens, there's no one standard data format for MicroED, and various labs will rely on their own homegrown conversion scripts to convert their raw data into some format recognized by their choice of data processing software. There is a different approach possible with dials, and that's that the package is extensible to read new formats. Actually, it's a feature of the Diffraction Experiment Toolbox, or DXTBX, which is a library used by dials. And here's a MicroED example to illustrate what I mean. In this case, I was sent images that had been recorded on a TimePix detector with a really minimal binary format. And a quirk of that particular detector is that there's a central cross of pixels between these four quadrants. And this cross is formed of pixels that are 3 times wider than a normal pixel. And that means when you view the image, like the image array as it is here in using the ADXV package, you get a distorted view of the real space on the face of the detector, because it doesn't know that these pixels are wider. So you're not representing the detector space properly. And what people do when they have this kind of data, they often convert it. They use their own conversion scripts to sort of split these wide pixels into 3 normal pixels. They're therefore having to modify the original data array and write out the data a second time in a different format. The alternative possible with dials is that we just treat all this in the interpretation of the format. So I wrote a format reader that would simply take the 4 panels, separate them, position them correctly in space, and also mask out these pixels, which are no good anyway for profile fitting, because they're a different shape. So you'd mess up the shape of the profiles if you were using them for integration. So over the last few years, I've collected a whole bunch of MicroED formats, which are available as extension plugins in a GitHub repository. And you just need to run a simple command to install one of these plugins. And that's what was in the instructions for the tutorial, but I've realized that recently I actually got rid of that. I've put in, at least for these data, it's recognized directly by the DXTBX. We don't need to install the format anymore. But if you've got some other instruments, you may want to install one of these format classes. And then other more standard formats like Thermo Fisher's version of the MRC format. So if you use EPUD to collect the data, then that format is supported in dials already from the get-go. But people keep making new detectors, they make new instruments, they make their own weird new formats, and it becomes a real headache to support all of these. And particularly the electron microscopy formats tend not to have the ability even to to record all the crystallographic metadata. And when, or they might just be very general, like TIFF, which contains no useful diffraction geometry metadata at all, and can collide with other X-ray formats, so TIFF formats used by old rayonics X-ray detectors and so on. So supporting all this out the box is very hard. And I started to realize why developers of other packages decide only to support a very limited number of formats and force you to convert to one of those rather than trying to cover all the bases. And I went on a little crusade a couple of years ago to try to introduce standards for MicroED formats. And this was the slide that Clemens showed yesterday. The various EM formats here are like a zoo filled with really unfriendly animals. And I'm the frustrated zookeeper that keeps getting bitten by these creatures. And this on the right is a motivational example illustrating that. This was data taken from an IUCR workshop in 2021. This data set was recorded on a metal organic framework and provided in various different file formats, including SMV format, which is on the left, and MRC format on the right. And because I'd done all this work in DAOs, being able to interpret all sorts of different formats, I could read both of them. But what you find immediately is that the interpretation introduces an image flip in the y-axis with one format versus the other. And it's not that DIALS did anything wrong here. It's just the fault of a lack of any robust standard for metadata. And the really pernicious thing with this case is that it's perfectly possible to process either one of these data sets. And in doing so, you get exactly the same unit cell parameters, identical geometry refinement statistics, just a different crystal orientation and rotation axis orientation. And in the end, you find that the only difference in the process data is that the Friedel pairs of reflections are swapped. And that could be really nasty. If you were trying to use MicroED to do dynamic diffraction-based refinements to resolve chirality of a compound, it's completely possible to get an inverted result simply because of a stupid file format problem. So I've got no doubt one day this will catch people out. One of my goals is that development of a format standard for 3D ED or MicroED. And I think that's certainly not out of reach. So we mentioned what the problems with EM formats. Really another issue is that the lack of a standard format containing full metadata is a roadblock for data auto-processing. But the users will very rightly demand this as data collection gets ever faster, and particularly as there are more and more automated data acquisition methods, like the rays thing that was shown yesterday, and others that I've heard about. So pretty soon we're going to be awash with data, and we won't be able to process it unless we can keep track of the metadata properly. And in the X-ray world, they've basically solved this. They've had committees who have met over many years to agree standards. And I don't want to join a committee. It doesn't sound like a lot of fun, but luckily they've done everything for us. So there's an NX-MX standard, which describes diffraction experiments. And that is a particular flavor of the general Nexus standard. And Nexus files can be represented using standard HDF5 storage technology, so HDF5 files. There's also an NXEM standard that contains additional information about electron microscopes, so it'd be possible to bring in other information about the experiment and record it in the same file. So this was work that we published a couple of years ago, showing how adopting those standards enabled us to do auto processing of dials of data using ZIA2 running the dial software at the EBIC facility in Harwell. I think Clemens showed this slide as well. So this is a few notes about the data auto processing for EBIC. This was made by Marko Petrovic, a postdoc in my group. and he's developed this AutoED package. And what we've got is that electron diffraction data is being collected very rapidly on the singular detector on one of the microscopes at EBIC. And this does have some useful metadata, but it's incomplete. And in particular, we need the beam center to process the diffraction data. And this is missing from the files as they come off the detector. The detector doesn't know where you put the beam. But AutoED is running. It's running on the Diamond file system using a watchdog script to look for new data sets appearing. And as soon as one comes in, AutoED will fire up a series of processing steps. Firstly, it will use various algorithms that Marco implemented to identify the beam center in the data. It will package that and other metadata into a new Nexus format header file for the data set. And that's done by a Python package called NextGen, which is developed at Diamond Light Source for its MX beamline. So it's not a homegrown thing that we've invented just for this, but it's part of the overall framework for data auto processing in Diamond. And once this data is ready in Nexus format, AutoED will run the auto processing using ZIA2. And that's also a standard package which is developed at Diamond Light Source and has been used for decades to process MX data. This is all done on the Diamond cluster for high throughput processing and returns to AutoED, which will produce a results page with a nice way of summarizing the various data sets that were processed. This next-gen converter now does also work for MRC format files, but Marco told me this morning it's not quite set up to work for those within the AutoED pipeline yet, but this could be implemented if there is interest. One disadvantage with the MRC or other formats is that you would have to copy the whole data set again into this new format. So you're duplicating the space. Whereas with this setup with HDF5, we're writing only a very small additional header file that just describes the metadata for the experiment. Anyway, that's how things are currently set up at EBIC. Going back to Dial's command line processing, let's assume we got the data into the software. The first thing we need to do with that is find spots on the images. So Dials was written with photon counting hybrid pixel array detectors in mind, like Pilatus and Eiger used on MX beamlines. And the default spot finding method is optimized for that kind of data. So here's an image from the singular detector, which is also an HPAD detector, but being used for MicroED. This, I'll just, click through. So showing that the standard spot finding method goes through a series of steps which kind of identify the likely location of the spots, finally going down to a binary maps showing where the strong pixels are and where the background is. And then if you overlay that on the original image, you can see that nicely the real spots has been picked up by the spot finding method. Now, it took me quite a long time to realize that the HPADs used in MicroED are not actually counting detectors. So I guess I was laboring under the illusion that because they were photon counting, they're also electron counting, but it's not true, because individual electrons scatter sideways in the silicon sensor, and typically counts will be registered in the cluster of neighboring pixels. And you can see that with very, very low dose imaging. So this is an image taken from a region from a time-based detector. It's not the singular, but the same thing applies for the singular. And if you turn the dose down real low, you can see the individual electron events. And then we wrote a script to collect all of these and count the number of pixels that are lit up on average per event. And the average for this detector is 2.9. So the gain is set as at 2.9. It's not a one-to-one counter. So in this case, there is It doesn't quite follow Poisson statistics. There's a little bit of variation in the signal per event. So stats are slightly worse than the true counter. Nevertheless, the standard spot finding algorithm works well in this case. The contrast is if you've got a different type of detector, like this is a C to D, so it's an integrating detector used in quite popular for MicroED. And this is actually the same crystal. So this was on the microscope when both detectors were mounted, and David Owen at EBIC was just able to swap the detector out, look at the same crystal. It's even the same spots, but the image is rotated 90 degrees in this case. If we go through the same set of steps for the spot finding, we see that the algorithm isn't really behaving well. It starts to break down, and at the end, we do find the spots, but we also find a lot of noise from not real spots, just picking up noise in the background. And if we zoom out, look on a wider view, you can see it's much more obvious here. We've got all this noise, it's even picking out sort of features of the detector. And this will make it quite hard to index this diffraction data. I spoke to Robert Bürker, who was in Hamburg at the time, now working at Rigaku, and he pointed me towards papers describing the Peak Finder 8 algorithm used in the Crisfell package. And that gave me the idea for a new spot finding method in dials called the radial profile algorithm. And this works much better for integrating detectors because it doesn't assume a model for the statistics. It isn't, there's no assumption of Poisson statistics. It just works with whatever was actually observed. So if I click through this is the result using the radial spot finder, radial profile spot finder on the same image. So flicking back, you can see it's finding the spots, but doing a much better job of avoiding noise. So this is the algorithm which will be used in the walkthrough and tutorial. So yeah, beam center is another problem. That's a problem for MicroED because moving the beam is an experimental variable rather than just something that's fixed by the beam line, as in X-ray MX. In the tutorial that we're going to present after this, it used to involve kind of looking at a spot, finding guessing its coordinates or reading them out from the bottom of the image viewer, doing the same for another that looks like the Friedel pair, and then calculating the intersection between them. As a simple improvement for users, I've implemented a simple line profile tool in the image viewer that lets you do that much more easily, and you can just copy out the value for the midpoint straight away. But it isn't automatic. But almost immediately after I'd implemented this, my colleague Marco contributed 2 new methods to the program, dial search beam position, which were specific for MicroED data. So one of these methods, the midpoint method, works very well if there's a high background. And what it does is it takes an average over a stack of images and then projects that onto X and Y axes. And then it looks for lines of equal height on either side of the projection, sort of iso contour lines, I guess. And then by calculating this at a few different heights, it then takes the average central position and determines the midpoint. So this works even when the center of the image is obscured, which is, as in this case with the singular detector, there's a dead region between modules, and the algorithm is able to cope with that. But the second method, the inversion method, seems even more powerful. And in this case, a maximum pixel stack is made, which really highlights the strong spots over a number of images. And then that's projected onto X and Y axes. And you compare the 1D plot then with its own mirror. And the idea is that you look for a point at which the image and its mirror best overlap, because this is then the point where the Friedel pairs are matching best. So this is like an automated version of the line tool procedure, except rather than limited to just a single Friedel pair, it's using all of the data in the image. So these are good. However, for the tutorial data, I've discovered that the automated beam center determination methods don't work well. So that's something I have to discuss with Marco. But for the tutorial, we'll use the manual tool instead. The issue with rotation axis orientation is that it's easier than X-ray beamline. You can just go and look at it. You can take a video of the goniometer turning as the experiment is collected. But in an electron microscope, it's much more complicated. It can move to various different orientations at different zoom levels, and all of it's happening in a box that you can't see into. And some microscopes, I guess they try and compensate for this at different zoom levels. But because of all the image format woes that I mentioned, the metadata for this doesn't usually tell us what that orientation is. And then the other issue is not just the orientation, but because that Ewald sphere is flat, it isn't easy to distinguish between left-handed and right-handed rotation around the axis. Whereas with X-ray data, this is immediately obvious. And this little figure explains that. We've got a set of points in reciprocal space in MX or X-ray crystallography. Maybe these points were recorded on 5 separate images, sort of rotated around this way, recorded on these 5 images, one after the other. If we got the assumed direction of rotation correct, then that's nice. They all line up in a single line in reciprocal space. But if we got the inverse rotation, they don't line up in a single line. They form this sort of curved shape. And then that's very easy to see using a reciprocal lattice viewer. Conversely, with MicroED, they're all recorded on this one image. And if you've assumed the wrong hand of rotation, they're all recorded on a different image. It's just a different orientation in reciprocal space, but it's difficult to tell which is correct. But when the axis is grossly wrong, it is obvious to see that in reciprocal lattice viewer. So here we're looking down the assumed rotation axis, and in this case, the rotation axis is we're completely wrong somewhere. And what we see is that the points are just mapped out into rings around that rotation axis, not into a proper lattice. And then previously in DARS, we were relying on prior knowledge or forms of guesswork based on the images to figure out rotation axis. But there's a really nice algorithm that Lukáš presented yesterday for automating the search, published by Ute Kolb and implemented in PETS, and also the ED Tools package. And I took the ED Tools version because that was open source and ported it into the DARS framework. And what this does is it makes a cylindrical projection of vectors, reciprocal lattice vectors at each orientation. And if the orientation is wrong like this, you get a weird blurry map like this. But when the orientation is correct, the map is very clean. And you can use this fact to automatically search for the correct orientation of the rotation axis. This does need pretty good data from spot finding, but when it's got that, it's sensitive enough to distinguish between the correct axis here, where we've got the highest value of this metric, versus its inverse. Mentioned that the diffraction geometry refinement is difficult. The unit cell from indexing in MicroED often has a very large error. It's partly because it absorbs error in detector distance calibration. And the flat Ewald sphere in MicroED means that the unit cell and detector distance are almost perfectly correlated. So if we've got a 1% error in the detector distance calibration, but fix that distance during processing, we just get that 1% error appearing in the unit cell instead. I should give a shout out to the LDCO team. I've been processing lots of data with their ED1 diffractometer recently, and this thing has no post-sample lenses at all. And I have to say that clears up all issues with the unit cell. Well, you've got two features. You've got the fact that the detector distance is fixed and known, So you don't need to ever change that. And you've got the fact there's no post-sample lenses. And I find with that you can get unit cell results that are as precise as you get with an X-ray beamline. So all of this stuff is improving as the technology progresses. So we can't freely refine unit cell and detected distance simultaneously, but if we know what the cell should be, so it's a known crystal of something, then with dials we can use a restraint to the known value, which is a way like adding extra observations into refinement. This breaks the high correlation between the detected distance and cell parameters. To make a restraint, it's a bit fiddly. You have to make a text file containing this kind of information with the unit cell values, and then a set of sigmas which describe the strength of the restraint. And smaller values here force the cell to be closer to the provided values. So this is used in part of this tutorial, which is on the dial's webpage. Because the detector distance is wrong, and it exists in the image metadata at least, but it's been recorded incorrectly, which is another issue if you've got homegrown conversion scripts and relying on like lab notebooks and things to record values. In this case, it's recorded wrongly in the data, so we use the restraints to force the cell towards what we knew it should be, and then read off the detector distance. And as you might expect, if you're restraining the cells, it will tighten up the observed distribution of cell parameters. So these plots are produced by the program dials.cosim. And these are using the 18 data sets that form part of this tutorial of the MyD88 domain. These plots look quite similar, but if you look at the scale in the x-axis, you can see that the distribution with restrained refinement is very much tighter on the right, with sort of a 2 angstrom range in the b axis rather than 4 angstrom. And there's still quite a range here because this is being driven by the data. The data from the different data sets here is different. So it's not the same as just fixing the cell to a single value, but it allows a little bit of freedom. And unsurprisingly, if you do this restrained refinement, then the results of unit cell clustering in programs like Blend and COSIM are quite different. But is it a better description of the population of cells? That's a bit of an open question because, at least in this case, the restrained refinement was done separately on every data set, which meant that each data set ended up with a slightly different detector distance. And maybe you'd think that's not really realistic either. If you collect the data all on the same day, one after the other, without changing settings, then the detector distance should be the same. So I guess with anything, I would say if you can, and you should try to determine the detector distance really accurately, calibrate it with a very good diffraction standard. And if you know that that does not change, does not drift with time, then determine it and fix it and keep it at that distance and don't let it refine. So a few slides on multi-crystal methods and dials. Multi-crystal information can be very helpful at different points in data processing. At the early stages of processing, you can use multi-lattice indexing in dials, and this is often useful in nanocrystal data where quite often multiple crystals are hit by a single beam. So being able to index robustly multiple lattices and single data set is important. Again, at the end of processing, if you jointly scale and merge data, this will help with the limited data completeness. And like Lukasz says, it also averages out some errors that are systematic within the data set. It's not exactly a correction for dynamic diffraction problems, but if you have a lot of data sets and you average them out, it certainly gives you better data if you're using the kinematic approximation. And another thing we can do with the reciprocal lattice viewer, we can provide multiple input files, and that allows us to get an idea of completeness and favored orientation of crystals as we're collecting data as soon as we've done the indexing. So here again, these are the same 18 data sets used on the tutorial on the web page. If I have this option show in crystal frame selected, then these data sets overlay properly. And we can see that how accumulating more data sets fills reciprocal space. And we can see that it looks like there's a favored orientation of the crystals. So even after we get to 18 data collections, we haven't evenly sampled the reciprocal space. But it's given us a rough idea of completeness prior to scaling. After doing the processing and doing joint scaling, we can then assess multiplicity of the points using another tool, the CCTBX Multiplicity Viewer. And this gives us more precise information because it's aware of crystal symmetry and it's providing values for the multiplicity of the reflections at each point, not just a visual overview of the completeness. So let's say we've done our integration. A good thing to do before we do the scaling actually is after having done integration, we want to determine a best overall unit cell from multiple data sets. So again, I've got the same 18 data sets shown again. These plots are showing the unconstrained unit cell parameters in the C2 space group after individual geometry refinement of each data set. And there's a really huge variation, especially in A. We can see, from values from around 96 angstroms right up to nearly 108. And it's partly because these data sets are very narrow wedges, and we've not tried to correct for any distortions that might have been present in the data set. Using the program dials to theta refine, we can refine a single unit cell model against all of the integrated data. And this is the same thing that Lucas described yesterday as powder cell refinement. So what we do, first of all, we're taking the integrated data rather than just the strong spots from indexing, because the integrated data has better spot positions because of background subtraction that's been done during the integration. So we've got more accurate centroid positions. And then we perform this refinement that is using just the scattering angle, not the actual positions of the reflections, just the scattering angle of each reflection. Because then it doesn't matter about crystal orientation. All the 18 data sets can be put into one refinement job. And this shows the results. So here the lines are showing the error bar plus or minus 1 sigma of the best joint unit cell estimate from the diffraction data. We see we get much nicer distribution for all the dimensions, including the nasty one here. And this is quite close to the published unit cell parameters for this protein, but it's in this case it's slightly inflated, and I think that's because the detector distance was still a little bit wrong. So having determined the best overall unit cell, the final part of processing is the scaling. And dial scale is quite nice for jointly scaling multiple data sets. So Lukasz mentioned the trend towards including very large numbers of data sets in data processing. Dials is quite good at that kind of approach to MicroED. So here this is just 18 data sets. When I'm talking about lots, I'm talking about over hundreds or more. But you get the idea with just these 18 data sets. One of the features that DIALS has is that it can quite rapidly rescale if you've added or subtracted individual data sets. So that makes the whole process of culling data sets from iterative scaling jobs a bit faster. Here's plots of I over sigma and scaling for those 18 crystals. So we can see there's a bit of loss of signal to noise for each data set during data collection, probably due to radiation damage. But in this case, the automatic filtering was done of the data set of the individual images using CC half metric. And this this has removed the worst images. And using this plot, you see there's still some images that have quite high R merge values for those specific images. But removing those images apparently doesn't make the CC half, including those images, doesn't make the CC half significantly worse. So they've not been removed by the automatic procedure. So anyway, this kind of automated scaling seems to work quite well. And from that, we're able to solve that structure. And then just finally in the talk, I want to show some slides on the use of dials for serial ED experiments. And so, yeah, why would we want to do serial ED? Well, I guess it's for somewhat similar reasons for doing it as SFX at the XFEL. You want structure determination from nanocrystals of beam-sensitive materials. But in a ED is really advantageous when the amount of material is limited. So rather than sort of spraying it all over the place with this injector system, so it's a bit rude because these are highly advanced pieces of equipment, but they're very wasteful of the sample in the XFEL. Whereas on a microscope, you can collect all of the nanocrystals laid out on a grid quite nicely. It's also one negative I should mention compared with the XFEL with an injector is that we still get the issue of preferred orientation with a grid, but you can work around that using multiple tilts. But a good reason for doing it is that you get higher resolution than a conventional MicroED experiment. Robert Booker has a lysozyme structure down to 1.5 angstroms using a serial ED. And it's even possible to do time-resolved experiments, apparently, down to about 50 femtosecond resolution in theory, but you can't go lower than that due to the difficulty in making a bunch of electrons that will stay together. And I don't know if this has been done on any biological samples yet. So there's various modalities for doing serial ED, and the combination with precession that's been mentioned is really interesting. So this is an area we want to look into with dials. The big problem is the fact that we only have 2D information on each pattern, and that was mentioned before. But if we have prior knowledge of the unit cell, the problem becomes just fitting the best orientation of that cell to the pattern. So it reduces the degrees of freedom. And there are 3 methods in dials that we can use for this. The real space grid search method that's been in there for many years and was used for X-ray data sets with very, very narrow wedge data sets at the synchrotron. And then 2 newer methods, one called low-res spot match and another called pink indexer, which was adapted from code that's used in CRISFEL. And we've been trying these out. Here's an example that was the data was collected at EBIC on the detector with the singler. And this is a triclinic form of lysozyme as an image of the crystal. Unfortunately, no scale bar, sorry. There's a represented diffraction pattern. It's quite nice. It diffracts very well. We lose a bit of some of the low resolution data because of this dead area. But it turned out actually that the low symmetry is actually quite helpful for indexing in this case, because the basis vectors then, the 3 basis vectors are quite distinct, and you're less likely to misindex with the wrong orientation of the cell. And we tried this data as a set of stills, and unfortunately, it turned out almost all the jobs failed in the unit cell refinement. But the reason for that, I realized that there's too many parameters in the triclinic space group when the data are really just 2-dimensional. And so we had to apply this unit cell restraint during refinement. And in that case, despite all the distortions that are present from post-sample lenses and whatever else is not set up perfectly with that system, this worked very well, and every pattern was correctly indexed, most of them by all 3 methods, over 80%. So the real space grid search method was the worst in this case. and both of the newer methods, low res spot match and pink index, so we're up at 99%. But unfortunately, working with Marcus Gallagher-Jones at the RFI and with people at the Stockholm Group, I see real life success with other data sets to be somewhat worse than this. So it seems like we had a particularly good case. And I think it's quite sample dependent. So the lysozyme crystal we had here diffracted very well, provided lots of spots, and that helps a lot with this kind of experiment. So that's the end of the slides. Just acknowledging everyone who's helped out over the many years. I won't list all their names. I'll just say that we're funded by the Wellcome Trust and our home institutions, Diamond, UKRI, and the Berkeley Lab. I guess I'll stop there. Maybe take some questions, and I'll get on into the walkthrough.
Questions for David? You guys just want to process data?
Yeah, let's do it. All right, I'll just get myself set up for data processing. Excuse me a minute. Right. Okay, I'm sharing my screen again. It's just an empty terminal at the moment. So let's see where we are. I am in this directory, so /data NCCAT tutorials. I then have, actually, let's go into a subdirectory. So yeah, I'll just say the images are here. So there's you'll have these directories too, which contain the images. So let's list one of them. Right, we've got a series of .img files. These are SMV format files. They're usually even at synchrotron beamlines, they're given the extension .img, but the format is known as SMV. And I have set up dials already. So you'll have a dials installed somewhere. And actually, I'll just show you setting the dials up. So I know where mine is. I need a dot to source a file. I will then point it towards where I know my dials is installed. Just double tab there to list the files that we've got. And I want this one, dials_env.sh, because this is a bash terminal, so that will interpret the commands in that file. If anyone uses C shell these days, there's also a file there for them. So I run that. It doesn't give you any output. That has thrown people in the past, but it's not supposed to give you any output. But to test it worked, I can now type in dials.version, run that, and I see some information saying, it's the one that was installed there. That's great. It tells me some information about the version number and the Python that it is using. So if I was to do dials dot and then tab complete a couple of times, you'll see all of these 90 odd programs that I showed in the talk. We're not going to use all of those. And maybe it looks a bit daunting like this, but one of the things that we try to do with these programs is provide a lot of online help. So for example, if I was to type just dials.import, one of those programs, and then hit enter, without providing any files, it gives us some help. So it gives us a usage string, a set of options that can be provided to the program, text description about what the program does, some examples, and then also if you take note of this -h, I'll show you the effect of that. If I type dials import -h and run that, then I get the same help message, but now it also provides all of the configuration parameters, that means the options to the program, within a certain set of levels. So the expert level of 0 would mean the basic parameters. And we can see that there are options like I can change the output name when the file, when the program runs, or the name of the log file, by typing in this type of command. If you're used to Phoenix at all, then it's the same setup. So to get this, to set this command, I would type something like, it would be output dot experiments equals, and then whatever for the file name I want. We can keep adding H's if we're masochistic. Actually doesn't do too much with 2. If I add in 3, I've got a whole load of other parameters, and these are the more expert level parameters. And the other thing I can do is add V's, which gives you a little bit of help about every parameter. It tells you what it means, and with a couple of V's, it tells you not only what it means but also what its type is expected to be. So with this stuff, you're hopefully able to figure out how the program works quite easily. Right. So let's go into what day is it today? It's the 4th. It looks like I made a directory already. I've gone into that directory, and I've actually processed these already today. But what we're going to do, I'll go into my subdirectory for the G4H3 dataset, and I'm just going to delete everything in that and reproduce it. Okay, so right, that's now an empty directory. Now, there's a description in the tutorial document that explains that reading this image format requires an extra step. I'm just going to show what happens if you try to import the images without doing that. So now I'm navigating through the file system. I need to go up from this directory, up from this directory again, and then I go into G4H3. I'm using my tab to do a tab complete, and I can see the images are named like this. But there's also this preview image here. So if I was to type in asterisk IMG, it's not going to work properly. Actually, I can just show you what happens. It doesn't like it, and that turns out because it's trying to read that preview image, which isn't a diffraction image. So it fails. And unfortunately, it doesn't tell you why it fails. To get around that, I'm going to use 4 question marks. This isn't a dials thing. This is just the bash shell that's expanding this string here into a series of strings that match all of the images in the data set with the 0 padded serial numbers. So if I import that, then it works absolutely fine, or happily, but it imports using this format SMV ADSC, and ADSC is the name of a now defunct X-ray detector company. So that's the clue that something's gone wrong. We're not dealing with X-rays. If I was to use the dial show program on the my spacebar is not working on the imported experiments, this program is will give you information about any of the dials files. In this case, it will show you the diffraction geometry, and each component of the experiment. There's a detector, there's a beam, and a scan model. Most of it's got right, but in the beam you can see it thinks it's an X-ray beam, and this is not what we want. And in fact, the gain will be set completely wrongly, and the data processing will eventually fail, or at least you'll get very bad or completely wrong sigmas because the gain is completely wrong. So what we're going to do is I need to set an environment variable, And I just need to remind myself exactly what the name of the variable is. And the reason that this is not easy is because we're dealing with the horrible world of nasty formats and conversions and things, and that's why it's not entirely straightforward to import this type of data. But at least with this environment variable, I have to just set it to anything. Doesn't matter what I set it to. I type in export force SMV as C to D equals 1, hit enter, and now repeat my import command. And now it's triggered the correct format reader for this data set. It says it's a SMV ADSC. It still thinks it's an ADSC because that's from the hierarchy of formats. It sort of belongs to the ADSC tree, but it says, no, but actually I'm from a C to D. So please set things correctly as if it was a MicroED experiment. So now we've imported. I'll just do my show command again, just to demonstrate that now we have a high value for the gain, which is correct for the C to D, and it knows that it's an electron source. Okay, so I list the files that are in the directory. I can see that we've got the log file that just reproduces what was on the screen. I think my spacebar is dying. I keep having to press it and it's not doing anything. Okay, so if I just shows that reproduces what you saw anyway on the screen. And then the other file, this imported.expt, contains the diffraction model, the models for the geometry, the detector, and so on. And this is now all we need in order to look at the images. So if I do dials image viewer imported, that pops up on the wrong screen. So I'll drag it over. Right, where's the control panel? There it is. There's the control panel for the image viewer. Now the image viewer, there's first thing I'll do is change the brightness. So I like to see, it's set at 10 by default here. I'll make it a bit darker. It's easier to see the spots when it's a bit darker. We can see that it looks like quite nice diffraction data. The spots are roundish. They're not sort of horrible or streaky. It's always a good idea to look at images throughout the data set. As we go through, we can see there's nothing kind of terrible happening. It seems like it's diffracting nicely. And I click right through towards the end. At the end, we see that, okay, so maybe the crystal was sort of lost, kind of, or it dies or something happens at the end. So probably those last few images we are not going to want to use ultimately. But we'll just carry on as it is for now. The image viewer will show things like the orientation of the rotation axis, which can be quite helpful. And I wanted to show. No, tell you what. First, I'll make a mask, because what's quite clear about these images is that we have a backstop shadow. Now, I wouldn't worry too much about that because it's aligned with the rotation axis, and because there's a kind of the reflections that are recorded close to the rotation axis are anyway thrown out by the scaling program, because these are reflections that are rather poorly recorded by the experiment. They tend to persist in the diffracting condition for a very long time, which means that the errors on those reflections are quite high, and typically they get thrown out. So quite often we don't worry too much about the reflections along the rotation axis, but it's kind of a big backstop shadow. We might be losing some low resolution reflections, so maybe we'll mask it anyway. So to do the masking, I use this actions menu. It's slightly wrong size here. It doesn't quite fit the text, unfortunately. And this is unfortunately a lot of the image viewers written with older technology that's not really not maintained as well as it could be. And we're looking to the future to replacing all of this with sort of web-based GUI programs instead. But at the moment, this is what we're limited to using. So I'm going to click on that Show Mask tool, pull that over to the side somewhere. Now it's a bit difficult to see the mask at the left edge of the image, so I'm going to increase the brightness even higher. Don't know if that helped, to be honest. Maybe kind of. I don't know. I can see roughly where it goes. And then I'm going to make this, again, this window, actually it did all fit. That's fine. Okay, so I'm happy with the mask tool window. I'm going to click on polygon. That's the easiest option because it helps. You can just trace round points where you think the backstop shadow should be. So I'm going to do a click here. Now you don't really see anything after the first click, which is a bit disconcerting. But once I do a second click, I can see that there's a line being formed. And I'll click kind of roughly around the edge and right out to about here. Done. And then having done those clicks, I have to click on this button again. This is a bit of a bug really with the tool, but it won't recognize the shape you've drawn unless you've unselected the mode. Now it's done that. I've got all the data written into this this field here, and I can save that definition of the mask to disk. There's also, you can save the actual mask itself. So that's the binary file that contains the zeros and ones that shows which pixels are masked. But actually, I like to save the definition because I can recreate that mask at any time again in future. And I don't have to carry around this larger binary file, just a small block of text. So I click save. And now if I get rid of that, click away, and if I show mask like that, you can see that that area that I've drawn is now masked properly. I'll go back to a more normal brightness, something like that. I wanted to show now the threshold pixels using the spot finding algorithms. So if I click on threshold pixels, this is with the default algorithm. And you can see actually it does a not bad job at all. It's certainly a lot better than the data set that was shown in the tutorial. And I don't know if that's due to something that was done to the data in the conversion into SMV format from the original format. But it does find spot positions, but it doesn't find all of them. It's a bit poor. So what I'm going to do is click through to a different algorithm, the radial profile algorithm that I mentioned. And we can see that it finds more spots. It's perhaps finding a bit more of the noise, but it's not finding lots of noise all over the data set. It's just doing a pretty good job at finding all of the diffraction spots. But there are other features or other options that I can provide to this algorithm. And one of them is a blurring filter, which tends to improve the shape of the found of the strong pixels, and also to clean up some of the noise. So let's zoom in on that one. If I turn the blur on, there's two options, narrow and wide. If I turn it on to wide, we see we get it sort of increases the size really the spot data is contained in, and it tends to find flick between it. It's not so obvious with this data set, but it tends to do a better job at finding most of the diffraction spots and excluding some of the noise peaks. So that's the usual set of spot finding that I like. Now, really the radial profile algorithm requires the beam center to be correct in order to get the most appropriate results, because it's based on looking at how the background falls off as you go out along a radius from the beam center. And I haven't talked about the beam center yet, but I'll try and get rid of the mask and get rid of the rotation axis. Beam center is shown by this blue cross, and it seems like it's about right. So it falls in the backstop shadow at least, and you can see that there's this halo of intensity around it, but it's not quite right. And we can I'll go to a good image. We can determine that using let's just find a good image first. Oh, that would have done. I want a more obvious one. So just paging through the images, that'll do, I suppose. So I'll turn the threshold pixels off. These spots, these are Friedelmates, and we know that the beam center should be at the position exactly between the pair of them. And it's close, but it's not quite right. So just to correct that, I'm going to use a different tool, Actions Show Line tool. I'll pull that over to the side here. Now I want to get it right in the center of this spot. In fact, maybe it's better if I turn the brightness down. I go right down to 2. We can see actually the spot is it's a bit bimodal. So we'll go for the center of the upper blob. And I'll try and click in the center there. Trying to be careful with the mouse, click there. And we see it shifted down to the right a little bit from where the supposed beam center is, and it writes the values actually of the beam center here into this field, which I'll just copy 1026, 1027.9. So 1026, 1028 really. Copy. Right. At this point, I'm going to exit, and I am going to find my import command again, and I'm going to use an option, and the option is fast, slow, beam center. Sorry, British English spellings. I can put equals and then paste in the value that I copied from the image viewer, and that's now that's run the import again. But before we look at it, I'm going to now also create the mask. So if I list the files that I have in the directory now, one of them is mask.fill, which was written out when I clicked on that save button in the image viewer. I'm going to use cat just to print the contents of that file. And it's very simple. It's those list of vertices that describe the polygon that I clicked out on the image viewer. So how do we mask the image? Well, I run a program dials generate mask. I need to provide the imported experiments file, and then just also provide that mask .fill file. And then the program knows what to do. It takes in that polygon and it creates a mask file called pixels.mask. But that's sitting separate to the data. We still want to actually apply that mask into the data set. So there's a separate command for that, which is dials apply mask. Give it the imported experiments. And I'll say the mask is the pixels.mask file that we've just created. Hit enter, and then that tells me that it's written a new experiments file called masked.expt. So in this one, we also, because we imported with the correct beam center, we should have everything correct. So I'm just going to take a look at it. Masked.expt, open that up. Of course, it opens on the wrong screen. Pull that open. So I go right into the beam, hover over the blue cross, and at the bottom of the image viewer, I can read 1026, 1028. I think that was right. That's what we wanted it to be. I can show that the mask is now saved with the data. And if we look at the radial profile with the wide blur, we can see that these are the spots that we're going to find on the next step, which is the spot finding step. Okay, so happy with that. So we exit. The spot finding program is just, it's unimaginatively named dials find spots. At least it's easy to remember what names dials programs are, because they're named after what they do. I want to give it the masked.expt. Now I need to tell it, I want that threshold algorithm equals radial underscore profile blur equals wide. That's all we wanted. I hit enter and it goes ahead, shoots through it all. So it gives you a list of the number of strong pixels first found on every image. And at the end, it glues those pixels together into spots. So it's turned them into just over 2,000 spots, and then does some filtering. If there are spots that are particularly small or particularly big, it doesn't like them, so it chucks them out. Also, if there are spots that have quite a different, if the distance between the maximum pixel and the center of mass of the spot is more than 2 pixels, it says it doesn't like that. It's a weird shape, so chuck that one out too. And prints a little histogram of the number of found spots at the end. You can see it sort of it drops down a bit, comes back up. It's probably just due to the different lattice constants and different orientation. But at the end, we have a serious drop off, and there's no spots at the end, which is kind of what we saw from the image viewer. Okay, but the next step is to open that up in the dial's reciprocal lattice viewer. So what did we have? It was masked and strong. So this viewer takes both. And if we open that up, I will fiddle with a couple of bits. Maybe I'll make the marker size bigger, make it easier to see. Something like that. If I rotate the reciprocal lattice around, I can see that there are orientations like this that line up very nicely, where I'm looking down columns of spots, and there's very clearly order to this. This lattice is clearly ordered, and that gives us hope that this will index correctly. There's some kind of funny features, and these might be due to very, very big spots. So some of the low resolution spots on some images were quite big. And this was also a spot that's close to the rotation axis. I can show that. Oops, didn't mean that. Show rotation axis. So this reflection, or there's a reflection around here which stays in the diffracting condition for a very long time. And probably it's being found multiple times on different images, and it hasn't been able to glue those together. So you've ended up with this sort of structure of lots of different reflections, kind of in a weird halo around the spot. If you were really interested, you could middle click and drag, go over to that set of that cluster, and then if I do label nearest point, it will tell you exactly where on the image it is. It's on image 24. Between 23, 30, 23. There's quite a lot of, actually it's mainly on image 23.5 or something. So maybe there's a little cluster of points around on that image, and you can see the XY position. So you can go back to the images and see exactly what that spot is if you're worried about it. But here I'm not worried at all. So I'm going to just get rid of that. The one thing I wanted to show the rotation axis finding program. Because we think that rotation axis is correct. If I inverted the rotation axis, like I said in the lecture, I mean, it's quite possible to find an orientation like that where it lines up nicely again. So you would be able to index it, but it would be incorrect. But let's just I won't show you. I won't upset the. I was going to upset the axis completely and show the rotation axis program working on that. But I think for the to save a bit of time, I will just run the program on the file that we have at the moment, just to get the plot out really. So where are we? Masked, strong. Run that program. It chunders through. At the end, it tells you what the rotation axis is, which is basically the same as what it was at the beginning. I thought it printed it at the beginning. It doesn't. The rotation axis is along the x-axis at 100, and the search has found it just 1 degree rotated from that, and written that out into a new file, optimize.expt. But what this program also has done is create 2 image files, which I can open using whatever image viewer you have on your system. If you've got Ubuntu on WSL, then it will also be EOG. We'll open an image. And if I paste the image file name in, you can see the that cylindrical projection at the orientation it likes best, and then also this plot. And we can see here it's very obvious that it's the rotation axis position is around the original 0 degree position, and the inverse is it's not even the second highest peak actually. All right, so I don't need to use the optimize because we know it was correct already. What I want to do from this point is just index the data. And the lattice looked nice in the reciprocal lattice viewer. I don't have any reason to suspect that we'll need a fancy algorithm or anything. I can just use the defaults. So I'll give it the 2 files, masked and strong. But the one thing I do have to always do with MicroED data is fix the detector. And fix the detector distance, that is. I can still allow the detector to slide around the beam and also to rotate around the beam, but I don't want it to allow the distance to drift, refine at all, because it won't be able to do that and refine the unit cell at the same time. So I'll run this. It does a 3D FFT on the reciprocal lattice peaks, and then finds the real space lattice from that FFT, and then FFTs that back to give you the reciprocal lattice. And you can see what it's found is, but by the way, it will always index in P1 unless you provided a different space group. If we look at quickly look at the output, it provides RMSDs in X, Y, and Z. So that's the root mean squared deviation between the observed positions of the spots and the predicted positions of the spots given the lattice. And these are not great. They're not unreasonably high for MicroED data. For X-ray data, we'd expect to see values of down to 1/3 of a pixel or less, but MicroED, all the errors are higher, and this is no exception. But we can accept this. And what I'll just quickly do is look at the indexed file, we see that we indexed 83%, which isn't too bad. Could be higher. There we go. We see there is a bit of, unsurprisingly, that weird feature that might have been points around some big spots. That's not indexed by anything, but the index points, they come up as yellow. I can now show the cell, and that helps me align the lattice in various orientations. And we can see that this has done probably a good job. All right, so we indexed in P1. If we look at the lattice constants, you can see that two of the angles are very, very close to 90 degrees. So we would expect monoclinic symmetry. But we have a tool to try out the various symmetry possibilities from an indexing solution. That's this one, refine Bravais settings. And again, it's a refinement program. It's going to refine the lattice. So we have to also fix the detector. Now I think in more, maybe not in this release, in a new release of dials, I've made this program no longer refine detector distance at all. It only refines the unit cell, because it doesn't help to refine the detector distance even for X-ray case. So there's no point in having it do that. And with that, we wouldn't have to then add in the fix distance option. But I think at the moment with this version, it's not quite there. So I'm going to run it with that fixed distance. And in this case, there's only two options. There's the original triclinic solution, and then there's the monoclinic solution. And the main things to look at are metric fit and RMSD. Unfortunately, with this case, we don't have many solutions to compare. Normally what you would see is you can go up solutions with increasing symmetry, and you look for a point where the metric fit suddenly becomes much larger, or where the RMSD suddenly becomes much larger. In this case, we don't have that, but we can see that Dials is recommending both solutions as quite possible. So we're going to assume then that the monoclinic solution is correct. And it has written that out to disk, Bravais setting 2. And I could continue here by re-indexing the indexed reflections using this change of basis operator in order to fit with that Bravais setting 2 description of the crystal. But that's complicated. And this is always a sore point in tutorials, especially when you've got lots of options. So I'm going to cheat, and I'm just going to run the indexing command again. But this time I'm going to say, I want the space group, P2. We'll run it. And now we get, immediately we get the P2 solution. We've got the unit cell. The RMSDs look slightly worse, which is not a surprise because we've now got constraints on what the unit cell can do to fit the data. So now I will move on to refining the solution. We've got the refine program indexed.xpt, index.refl. Again, I'm fixing the detector. I run that, and this runs two modes of refinement. In the first refinement, it refines a single model for the crystal to fit all of the spots in the data set. And the second part, it takes that as the basis and then refines a model for the crystal that allows it to vary slightly in a smooth way. So it allows for any changes in the orientation of the crystal during data collection, or even changes in the unit cell parameters. And so that's why at the end we get lower RMSDs than we had before, because we've allowed this model to adapt to the data. There's a viewer for checking the results of that process. So you can use this Dials plot scan varying model. It creates two more graphics files. So I'll open one. And we can see that it thinks that to best fit the data here, there's a slight change in the A-axis, there's an increase in the B-axis, bit of a wobble in C, slight change in the angle. None of these are probably realistic, and it's most likely accounting for some other errors in the experiment, like some unaccounted for distortions coming from the lenses. But what we look at is that they're not enormous changes, so they don't look too worrisome. If I page over to the angles, you can see there's a bit of a drift in three angles around the supposed orientation. But again, it doesn't look too severe, so we're happy with that. The next step is just to run the integration program. So there aren't any modifications that I have done yet to the integration program for MicroED data. I don't know what it needs yet, really. We think that the profiles are different in MicroED compared to X-ray data for various reasons, but it seems like the 3D profile fitting method that XDS and Dials both use gives reasonable results. So at the moment, we haven't got anything other than that. Now, there's a whole load of errors printed out, which is just something to do with one of the libraries that Dials uses. So it's complaining that we're using some deprecated function. So just ignore all that. I'll just get right down to the bottom. Right, so the first stage of the processing, it creates profile models for each region of the detector and each position in Z or image number in the data set. And then in the second part of integration, it goes ahead and just uses those profile models after we get past all the error printout. It will use those profile models to do the integration. And it's finished already. Okay, so we've got integrated refor, integrated.expt. Just for fun, if I open the image viewer again on the integrated files, you see a slightly different kind of view to before, because now we're seeing every reflection, not just the strong ones, but we're seeing all of the weak ones that the integration program has integrated as well. And we can look at things like the center of mass of the spot compared to the predicted position for the spot. We can check that those things are kind of close enough. We don't think anything has gone horrifically wrong. It's actually pretty good in most for this case. All right, so that has completed up to integration for that data set. But really what we want to do is solve the structure. That's what we want to do. And we have also the results that I prepared earlier. So we have 3 data sets for which to do this. And what I'm going to do is jointly scale them together. So I'm going to make a new directory. Let's optimistically call it solve. And I'll just change into that directory. And the first thing I want to do is run that 2θ refine program, which will allow us to refine the unit cell using all 3 of the data sets. And what I need to do with this program is point it at each of the data sets integrated data files. So I'll go into, I want that one, integrated. I can use it's a bash shell trick here again. If I do that with the curly braces, it would expand into both of those file names. And then I can do the same again, but for the other data sets. Where are we? 4i2. And the last one, G5, E2. Okay, so that was very quick. What's it done? It has performed 3 steps in the refinement, so it was quite close to. I think it didn't have to do much. Let's say that, but it's given us a final refined crystal model with this unit cell in space group P2, and prints a bit more information as well, and with the full estimated SDs, which can be useful for um, tables when writing papers. But the important thing is we've got that cell written into this new file, refined cell.expt. And now I want to do the scaling. So to run the scaling of all those data sets, I don't need to point to integrated.expt for each of the data sets, because actually it's all contained in one file. It's this refined cell.expt. So I provide that file, but I do still need to point it at the reflections for each of the data sets. So let's go up to this one, integrated.refl, and then what was it, 4i2 and G5, using tab complete to my advantage here. So now we're giving it the refined cell, which contains also all the other models, of course. It's got the detector model, the beam model, and so on. Giving it the 3 data sets. And just hit enter, and that's performing a standard scaling model. Again, with dial scale, we've not made any real adaptations to this for MicroED data. It's just doing the same job that it would do for X-ray data. Once it's run through, it gives you a little table to look at, but I prefer to look at the graphs, which are recorded in the HTML file. So I will try and open that in a browser. On Ubuntu, I can use this program, xdg open, and just give it the file. I think it's like the open command on a Mac. Just allows you to open a web page using your favorite browser. So let's have a quick look at this. At the moment, we set no limit for the resolution, so it's processed right out to the corners, where of course completeness is really low because we're going right out into the corners where there's where you can only record a very small amount of data. But it looks like it's actually diffracting still quite reasonably, even out to the very high resolution. Yeah, one thing that I always look at is the R mesh value within the inner shell, because this tells you really how well the very best, strongest reflections in your data set, how well do they agree with each other? And it seems like they agree with sort of 20% error. So it's kind of, for X-ray data, that would be terrible. And you'd be thinking about having the wrong space group assignment or something like that. But again, with ED data, it could be quite tolerable. But the CC half looks a bit low in that low resolution shell, and this is something that we really would want to see at quite high values. So if we look at the plots, maybe we'll figure out why. So CC half plot here looks really weird. It goes, you've got decent diffraction to maybe 0.9 angstrom, something like that, and then the rest of it just looks like noise. And completeness, we can see it drops off like linearly as you go out into the corners of the detector. And if I look at the analysis by image number, we start to see where some of the problems are. So of those 3 data sets, that first one that we were processing, we saw that the images were, it looked like the crystal had disappeared at the end. And that's what we see here. The scale factors drop right down to nothing. And the R merge by image is also shooting up, and again with the second data set. So let's try to run another scaling job, setting a few options to try to account for this. So what if I can do this? Let's do it like this. I'll get my scaling job back. So just doing arrow up to bring it back in the history. And perhaps first of all, I want to set a resolution limit. I'm going to be optimistic and say 0.6. And then I want to exclude some images. So the format for that is I use 3 numbers. The first number refers to the dataset number printed at the top of the plot here. So I'll start with 0, colon, and then I can actually drag out on the plot to kind of zoom in a bit. And I'll say maybe from image 33 it starts to get pretty bad. So let's say 33 to 38. I guess that's the last image. 33, 38. And then again, I'll just auto scale that to go back. Look at the second data set. Data set 1. That looks like image 72 to 77, maybe. Oh, well, the problem is, I think actually it's renumbered the images to start from 0 from the very start. So what I need to do actually is look at the mouse over text. So it says actually it's image, this one 72, that's actually image 34, considering just that data set on its own. So I'll do 34 to mouse over here, 39, whatever it is. And that last data set, it's a bit funny at the beginning. Maybe the crystal wasn't quite in there, but other than that, it looks all right. It maybe dies off a bit at the end, but let's just try this job. Right, it's complained. Why did it complain? Oh, because it thinks that this is because I forgot to write exclude images equals. Actually, I don't need to, I can either write it twice or I can just put it as one command with a comma. So let's do that. Okay, so now it runs again. And it writes out to the same web page. So all I'm going to do is reload. And now we've got, well, the R measures now it's down to like just 9% in the inner shell. That looks a lot better. CC half now maybe looks more believable. Let's have a look. If I look at the plot, that looks more like what I'd expect, with a fall off of CC half down to the point where the data are weak and you're not getting much more usable information. So sort of 0.6, maybe that's a bit optimistic still, but it will do. Completeness was still dropping off a bit in the corner of the detector, so actually our completeness has gone down to 44 and in the outer shell. But otherwise, it kind of looks okay. I don't know whether to maybe I should increase that to 0.65. No, let's leave it at 0.6 for now. So what I want to do is just finish with trying to solve the structure. So we've scaled the data. Now I want to export, but the standard command here would export to MTZ format for MX data, which we don't want, of course. So I need to say format equals shell X, and then takes in a composition string. And I think it actually defaults to CHNO anyway, but let's just put it in. And that will write out a standard, well, 2 files. It writes out the reflections to dials.hkl and a shellx instructions file to dials.ins, which we can just pass straight into shellxt. by typing in shell XT dials. And it looks like we know actually that the data's, I think it's paracetamol, right? This the tutorial data, and we know the space group for paracetamol, and it has found that solution actually in dials A. It's got the higher R1 value, and these are pretty nasty values if you're doing X-ray data. But as Tim and others have presented, it's acceptable for MicroED. Certainly at the very initial point of structure solution, with proper refinements, we would be able to bring that R1 down, and also in fact the atom assignment, because that's likely to be wrong. Let's look at the solution. I would use OLEX too, but for some reason the GUI doesn't work on Ubuntu for me, so I can't. But there's another viewer, ShellXLE, that I like quite a lot. And if I look at dials A, open that up, well, that looks like paracetamol. That's not bad at all. So, oops, losing it. So you would have to correct the atom assignments. I guess we need to change that. But anyway, that's we have successfully solved the structure based on combining the 3 data sets, and the statistics are not too bad after you've trimmed out the bad images. So I think I've been speaking for far too long, so I'm going to stop at that point, and give you all a chance just to try it out.
Looks like David.